Okay, so we just derived an expression for the general motion of a simple harmonic oscillator or a mass spring system, which looked like this. X of t equals x naught, which is the initial position, cosine omega t plus x dot naught divided by omega sine omega nt, where omega n itself is given by this expression, right? So, or more generally, x of t equals a cosine theta or a cosine omega t, b sine omega t, where omega is actually omega n. Okay, so in this little video, we're going to talk about, okay, what does this expression really mean? What does it mean? Okay, again, it's good to understand what it means, but the derivation itself is not necessarily part of the exam or going to be anything like that, but it's good to understand what this expression means. Okay, the first thing to understand, of course, is, well, of course, what cosine and sine looks like. So let's just draw those pictures just to recall what cosine and sine looks like. So cosine looks like this and then repeats after itself, right? So that's basically your cosine omega n t. If you plot cosine omega t as a function of time, that's what it will look like. And the period of oscillation of a cosine omega n t is 2 pi divided by omega n. Okay, so this is equals Tn, where Tn is the time period of oscillation. Okay, so Tn of free vibration. Okay, so we'll develop on that, and that's equal to 2 pi by omega n. We'll develop on this in a minute, but let me draw the picture for sine omega t. And it's gonna look essentially the same except shifted over, as you know, sine omega t. And so on and so forth. All right. So, and again, one period of oscillation, in other words, one full cycle of oscillation is this thing. That's again Tn equals 2 pi divided by omega n. Okay. So what do we mean by period of oscillation? It means time period after which time period for one full cycle after which things repeat, right? Everything repeats. And we've used the subscript n because it has to do with the natural motion of the system in the absence of external forces. So we might call this the natural period. Okay, and then we can define this quantity f sub n, which is essentially 1 over Tn, or omega n by 2 pi, which is also called natural frequency and measured in units of seconds, 1 over second or hertz, right? And of course, Tn is measured in units of seconds or whatever time is measured in. Okay, so this natural frequency, this version of natural frequency is how many cycles per second. Okay, so this is the natural frequency. That means how many cycles per second. Omega n is also called natural frequency, but it would be called the natural angular frequency perhaps. Okay, so omega n is natural okay. In the context of an exam, when we say natural frequency, just assume that it's Fn, unless we state otherwise. Sometimes you might say natural frequency omega n equals blah blah, in which case, of course, assume that it's omega n, right? So if we just say natural frequency in words, in terms of cycles per second, and we represent it in terms of cycles per second or RPM or something like that, then we just assume that it's Fn. Otherwise, assume that otherwise we will state explicitly that it's natural frequency omega n. Okay, so that's about the frequency of oscillation or the period of oscillation. That's basically related to omega n. And we notice that both the terms, cosine and the sine, have the same natural frequency or natural period. So the sum of those two terms will also, whatever that shape looks like, that curve looks like, the sum of those two terms will also have the same frequency or amplitude, right? So in any case, let's examine these curves a bit more. So cosine and sine have amplitude equal to 1, right? So the peak of these curves is basically 1 unit magnitude. Let's look at this expression. This expression, of course, is a times cosine, which means that if you plot a times cosine, this will have an amplitude a. If you do b times sine, it will have an amplitude b. But here we've just plotted cosine and sine. Okay, so the first thing we understood has to do with the frequency of oscillation. Let's now talk about, okay, first of all, what is the amplitude of this object, this curve, and then what does it look like? Okay, so what does it look like? So let's go back to x of t. So this is perhaps a longer derivation than okay. This is a mathematical trick. Let's just multiply and divide by square root of a square plus b square. This is to try to getting more intuition about x of t, getting more math intuition about the motion. Okay, so that's what we're trying to do here. So let's multiply and divide by square root of a square plus b square. So we get a over square root of a square plus b square cosine omega nt plus b over square root of a square plus b square sine omega nt. Now these two quantities are sort of interesting looking. They have an interesting property. So let's actually call this quantity, let's call that quantity C1 equals a square root of a square plus b square, and C2 is b divided by square root of a square plus b square. Let's do C1 square plus C2 square. So that basically gives us a square plus b square, a square plus b square in the denominator, a square plus b square in the denominator. And if you add this up, you get a square plus b square divided by a square plus b square equals 1. Okay, so basically these two quantities, C1 and C2, have the property that C1 square plus C2 square equals 1. Okay, so that actually suggests that we might be able to replace C1 and C2 with, what expression, what quantity has the property that, what quantities have the property that C1 square, what quantities C1 and C2 have the property that C1 square plus C2 square equals 1. We can sort of say C1 equals cosine phi and C2 equals sine phi, where phi is some angle. Okay, and then C1 square plus C2 square will satisfy 1. Okay, so let's actually plug these expressions into this guy. Okay, so what we have is x of t equals square root of a square plus b square, and then within brackets we have cosine omega n t cosine phi plus sine omega n t sine phi. And okay, that's sort of making progress. Now, if you recall your trigonometric identities, this identity has to. So what we have is, so let's try to simplify this expression using a trigonometric identity. So if you have cosine A, sorry, not cosine A, I shouldn't use A again. Cosine theta 1, cosine theta 2, plus sine theta 1, sine theta 2 equals, it turns out, cosine of theta 1 minus theta 2. Okay, so this is a trig identity, trigonometric identity. Okay, let's use that in this so that we get x of t equals square root of a square plus b square times cosine omega n t minus phi. Okay, so that's what that looks like. So what does this mean? This expression is now indicative of what this complex function looks like, what this function looks like. It's basically a cosine. X of t is a cosine or a sine, doesn't matter, with amplitude square root of a square plus b square. And then this is sometimes called the phase offset. Okay, so what does all that mean? So if you have x of t, a cosine omega t, b cosine sine omega t, then it turns out we have some cosine or sine looking curve like so, where the period is till Tn equals 2 pi by omega n. Okay, the magnitude or the amplitude is actually square root of a square plus b square, or for our purposes it's actually x naught square plus x naught dot square by omega square. That's the amplitude of vibration. This is x of t. And we have this quantity. So the peak, so I noticed that I put, instead of drawing a cosine with the peak starting out here, I put the peak a little bit away from t equal to 0, and the peak is actually determined by this quantity phi. This is the peak, and peak phi is basically phi over 2 pi is the peak, right? So and this is this phi is called the phase offset. Okay, so so this is basically a shifted cosine, a time shifted or a phase shifted cosine with this amplitude and this frequency. Okay, so this is the big derivation. Let me scroll back down. So this expression, a sum of a cosine with some magnitude, a sine with another magnitude. If the cosine and the sine have the same frequency, then what we've just shown is that a cosine plus a sine, independent of what magnitudes the individual cosines and the sines are, results in basically a shifted cosine with some amplitude that depends on both the amplitude of the sine term and the cosine term, right? So essentially we are saying x of t equals a cosine omega t plus b sine omega t is equal to a cosine-like curve that has amplitude square root of a squared plus b squared, same frequency as both the sine and the cosine, and then a phase shift, which corresponds to a time shift, phi over 2 pi. Okay, so that's the big expression. So the sort of summary is that this motion x of t equals a cosine omega t b sine omega t is still a simple sinusoidal or cosinusoidal motion, except with this amplitude